Professor Hans Irschik. His paper is co-authored by Professor Kromer and Dr. Zetterner, and the title will be Shape Control and Vibration Morphing of Pre-deformed Smart Structure. For the few who don't know Hans Irschik, in the meantime that he reached the computer, is a professor at Linz University, and is the inspiration of an Austrian center of excellence about mechatronic, and is among the other and many activities conducting one of the main editor of Acta Mechanica.
So, okay.
Are you comfortable?
Yeah, thank you so much. I hope I look comfortable for you. Thank you so much, Mr. Chairman Fabio, for this kind introduction. Ladies and gentlemen, first of all, I would like to express my sincere thanks to the organizers of inviting me to these lectures, coming to this wonderful place and to this distinguished conference. Thank you. And I, of course, would like to acknowledge the work of my co-authors, Michael Kromer from the University of Technology in Vienna, and Dr. Zehetner from this Linz Center of Mechatronics, in the course of which we have performed this work. We are dealing with shape control and vibration morphing, how it is nowadays called, also denoted as displacement tracking. And these problems are often treated so far in the framework of the linear theory of elasticity with actuating eigenstrain types effects. And I have provided some review papers on this topic in the abstract. And today we would like to extend this problem to the case where we start from a static pre-deformed configuration. So we will consider, for comparison's sake, a natural state of the body as a reference configuration, and from that the body will be deformed, possibly large, to an intermediate configuration, which we will take as a static configuration. And then from this rest situation, the body is, forces are applied to the body, and we want now, by additional smart actuation, force the body to follow some prescribed trajectories in space and time. This exactly is this vibration morphing problem, and if we would like to keep the body at rest, despite there are time-depending forces acting, one often speaks about shape control because the shape is conserved. This is not meant in the sense of automatic control, but should give a good insight into possibilities of automatic control. So now I hope that I understood right with going on. Well, I start with the fundamental equations, and our strategy usually is to study the problem in a most general continuum mechanics setting, and then by analogy apply it to structural applications. So we write down the local balance of linear momentum of our body, where P denotes the first Euler-Kirchhoff stress tensor, P0 is the imposed body force, ρ0 the mass density, both with respect to the places in the reference configuration. U is the displacement vector from that configuration, and capital diff denotes the divergence with respect to the place in the reference configuration. And we have prescribed some boundary conditions of place at part of the boundary dB1, and at the remaining part dB2 there are boundary conditions of traction. The asterisk denotes the given quantities. U is the displacement, N0 is the unit outer normal vector at the surface in the reference configuration, T0 is the imposed surface traction. This is the total solution, and we now split this solution into a intermediate configuration and some increments from the intermediate configuration. So the intermediate configuration is denoted by the subscript I, and we have a subscript plus for the additional incremental quantities, and particularly the displacements and the strains are assumed in the framework of the theory of the so-called theory of infinitesimal displacements superimposed upon a state of large strain. This is the mathematical framework we deal today. Sorry, this is wrong. Aha. I apologize. For the incremental infinitesimal state, we can also write down the balance of linear momentum. For the additional quantities, we have some additional prescribed entities at the boundaries, and since we start from a static configuration, the initial conditions are trivial. Now, we need some constitutive relations, and in this theory of infinitesimal displacement superimposed upon the intermediate configuration, we use linearized constitutive relations, and here for the first Euler-Kirchhoff stress in the following form, the AI is the fourth order tensor of elasticities in the intermediate configuration. Grad refers to the gradient with respect to the intermediate states. This bracket is the Grothin bracket indicating the mapping of the gradient of the displacement via the fourth order tensor of elasticities. And then there is additionally a smart actuation assumed in the form of an incremental actuation stress tensor of second rank. It might be more common to write down this linearized equation for the second Euler-Kirchhoff stress S plus, where we have another fourth order tensor of elasticities. You have here the deformation gradient in the intermediate configuration, Fi, and within the bracket, the symmetric part of this quantity refers to the linearized, linearized incremental strain, and the CIs are such that the symmetric part of this tensor product can be applied as well as the tensor itself. And here we have the additional smart actuation as denoted as SA plus, and we will assume this as a linear mapping of some non-mechanical fields like electric field or temperature. Yes, and we seek for these quantities then. There is a relation, of course, between the increments of the first and second order Euler-Kirchhoff stresses, which is given in this form, and which then in substituting in these relations shows a nice connection between the two forms of the elasticities, and showing clearly that, of course, those elasticities are non-homogeneously distributed throughout the body due to the pre-deformation. You see here the second Euler-Kirchhoff stress in the intermediate configuration. This is equation 12. I will refer to it. And we have additional relations for the actuating stresses. I'm sorry, this was not the right. Now I come to a mathematical formulation of our displacement tracking or shape morphing problem. we seek for a space-wise distribution of this actuating stress Pa plus such that the above initial boundary value problem for the incremental quantities resides in prescribed incremental vibrations which can be represented by a time-dependent field of displacement set everywhere in the body under consideration and for every time. So U plus shall be a given value set. This is our goal. And in order to reach this goal, we introduce an error displacement field, which is the difference between the actual increment and the desired set. Yes? And our goal is, of course, to make this error field 0. Then equation 14 will be satisfied. And the first direct strategy to do this is simply to substitute, to replace U plus in the above initial boundary value problem for the increments by the error and by set. And doing so, we obtain from the above equations the following relation. And the idea is simply, if I choose Pa plus such that the error here becomes such that the right-hand side here vanishes, then it is possible that the error field becomes 0, because we deal with a trivial boundary value problem. And substituting this into the boundary conditions and into initial conditions, we see that we must have two necessary conditions such that this error field can vanish in any way, namely that at the boundary where the boundary conditions of place are given, of course the desired set must coincide with the given boundary conditions, and of course that the initial conditions of set must be 0, otherwise we cannot have coincidence. And the remaining idea, so making the field equations for the error displacement to be trivial, leads to the following sufficient conditions for this actuation stress. You see here, the right-hand sides are given. We know set, we assume to know the given force loading. We can compute the right-hand side, and we find that this is a quasi-static equilibrium problem for this additional actuation stress, which represents a statically admissible field. Yes? And this is good because usually this has not a unique solution, and we can choose between the solutions. Of course, we are dealing here with an inverse problem, and inverse problems, the solution may not exist. Here it exists because we have found these relations, and it may not be unique, and usually it is not unique. We can play with these relations. And we can compute the same with the second Euler-Kirchhoff stress actuation, and I will skip the details. We come also to a nice representation in this SA plus, where here directly the second Euler-Kirchhoff stress and the gradient in the intermediate configuration appear. Of course, we are starting from possibly large deformed configuration, and we have to talk about stability. And therefore, we think of an alternative derivation which brings this effect into the play. And here we suggest the following. We apply a so-called Neyman integral to the error displacements. This type of integral has been used by Neyman originally in order to prove the uniqueness of the linear problem of elastodynamics. And we use this here for the error displacement. Yes? And we immediately see, since the error is 0 at the beginning, this Neyman integral is 0. And then applying, as usual, symmetry property of the tensor of elasticities AI, and applying the time derivative to this Neyman integral, we come to the following relation, to which we can apply tensor analysis. And here, in order to transform the integral over the body B into an integral over the body and over the boundary of the body here, this boundary. And we see immediately, if we choose PA plus as suggested before for solving this displacement tracking problem, then the time derivative of this Neyman integral will vanish. So the Neyman integral will be constant, and since it is initially constant, it will vanish. However, we have to keep in mind the following thing. In this Neyman integral, the first part is positive semi-definite. It can only be 0 or greater than 0, while the second part is not. So we have to require, in order that the Neyman integral, the vanishing of the Neyman integral implies the vanishing of the error, we have to require that the following inequality must hold. AI applied to the gradient of the error displacement, scalar product with the gradient must integrated over body must be greater than 0, and indeed this corresponds to the so-called Hadamard stability condition, which is in this theory also known as infinitesimal superstability of the intermediate static consideration. So we now have, we can also alternatively derive this in the framework of the second Euler-Kirchhoff representation. This is also a nice piece of work, and this piece of work leads to the following alternative inequality, which replaces the direct Hadamard condition for the first Euler-Kirchhoff stress formulation. Okay, I will not go into the detail of this here from time reasons, and I will only say that we now have found the following. If at the boundary, for the boundary conditions of place, the desired function set, field set, corresponds with the given boundary, incremental boundary conditions. If the initial conditions for set are 0, and if this Hadamard type condition of superstability holds, then in order that the additional displacement is equal to the desired one, the following equations have to be satisfied, and we have to find a solution of this static boundary, of the static problem, equilibrium problem. And we can do this by adding some fictitious constitutive relations and some fictitious boundary conditions of place, and find the solution which satisfies this. We can do this with conventional finite element problems, linear finite element problems. And now we would like to apply this to show an example. And the most simple example is the single degree of freedom oscillator, of course. Yes? Only one mass particle. Yes? Then in this, the stress, of course, is replaced by a restoring force. We assume, and the displacement is replaced by the position x of the mass. And we assume a restoring force of the cubic type here, of the cubic type. Yes, it is shown here in a non-dimensional form. And we split this x in an initial x and an additional x. And this is our restoring force here in the range of x we are treating. And we can immediately see that the linearization gives this form of the constitutive relation. So AI applied to the gradient of U plus is replaced simply by AI times U plus. And AI as a function of the intermediate configuration is given here. And we have shown it here in the non-dimensional setting. It has a positive part and a negative part. And the Hadamard integral is replaced simply by IAI, which is the slope of the restoring force curve, times U error to the square must be greater than 0. This means AI must be greater than 0. Then the intermediate configuration in our language will be infinitesimally superstable in this range, and it will not work in this range. And indeed, our example is the following. Yeah, the equations of motion are replaced to this one-dimensional case. And we wish now to have a shape morphing with Z. So our actuation force, which replaces the actuation stress, is given in this simply analogous form. Here we can compute it, we can apply it. Yes. We now assume that the given force is harmonic with frequency omega, and that the desired displacement starts from rest, has the double frequency, then the excitation frequency, and another pre-chosen amplitude. And the initial conditions are 0. We can obtain a closed form solution of this problem by Maple, and we can, to the force, apply a small disturbance and look what happens. And indeed, if we are in the left side where AI is greater than 0, so for intermediate place 0.5, here, no, sorry, here is for the intermediate smaller than this 0.58, yes, here in this range, we are here 0.5. The solution is the desired one. We choose a double amplitude and the double frequency of the given one. However, if we choose an intermediate configuration in the unstable case, then after some time the small error force causes, of course, instability. So, in a second and last example, I would apply this to, we can formulate this problem also in the form of the second Biola-Kirchhoff stress actuation, and I would like to show an example, a structural example for this. And we treat here a thermally buckled beam with fixed ends. Thermally buckled, it is heated, and the equations of motion are assumed in this von Karman type form, where the intermediate normal force follows from this integral of the square of the slopes, and some initial heating, mean heating of the beam. And we have hinged boundary conditions which are axially fixed. Then this is a well-accepted boundary value problem. M is the bending moment, W is the deflection. We have an actuating moment and an actuating normal force. And this is an interesting problem. You have here the mean thermal heating, and here the deflection, and here the normal force. And in this cusp-cut or fold catastrophe type solution, a small thermal moment would lead to a stable, large displacement near the first Euler buckling load. There is an unstable and a stable root also. And it is interesting to see that you can reach relatively large displacements due to heating being below the Euler buckling load here. So this is a well-accepted fact in thermal buckling. And now assume that you have some thermally buckled panel or structure, and you have a large pre-displacement, and now you would like to force to have here some to morph the vibrations or to suppress some vibrations. And then, sorry, and then, of course, we have to formulate the superimposed infinitesimal displacement initial boundary value problem. And we have to formulate, in analogy to above, the sufficient conditions for this shape morphing with Z. You have here the acceleration of Z, the Z, the initial normal force, some additional force. I suppress here the plus index plus is omitted. This is an analogy to the second Biola-Kirchhoff formulation for morphing. This is the actuation stress, again, a quasi-static equilibrium condition for the actuation moment here, second derivative 2 primes, as usual in structural mechanics. And one has to distribute this actuating moment in order to solve this equation. And if one, yes. Now, in order to check if this works, it is necessary to formulate this Neyman type integral appropriate for the beam. And you have here the dynamic part with the velocities, error velocities, and you have here part due to the bending and the part due to the initial normal force. And this part here is analogous to this Jn. And the first part in the Neyman type integral is analogous to Jm. And then it turns out that for a certain class of possible error displacements, indeed, this branch 1 I have shown you is infinitesimally superstable. There is another stable part, which, however, is not superstable, which throws a nice light on the meaning of the word superstable. And there is the unstable part here. The J is smaller than 0, and we do not recommend to work here. We would like to remain here. And then this means that I'm on this branch, and the initial normal force must be smaller than the Euler buckling load, but we are possibly on this branch, and everything will work because we are smaller than the Euler buckling load. We can compute this in a 1, 2, 3 or multi-mode approximation like in the first example. I do not go from time reasons into these details. So in order to conclude, we wanted to extend so-called shape control solutions to the case that there is a large pre-deformation. And we now in the next step, our group now in the next step will think over how to apply this in practice, how, for instance, to distribute the actuating moment such that these solutions can be satisfied. If we do not know enough about K, about Ni, about Q0 or Q0 or so, then, of course, an automatic control system must be added. And this automatic control system then has to be designed properly. But as a starting distribution for the actuator, which you have, of course, to distribute, not continuously, because usually one works with patches or other discrete materials, then it has to be studied how it works. So I hope that this has found your attention. I thank you very much, and I would be happy to answer questions. Thank you.
Any question in the audience?
Hans, would you please to answer a simple question? Why do you prefer to work in the framework of Lagrangian dynamics, not Eulerian?
Yes.
Why you don't use the Cauchy stress tensor? Is it some preference? I know what
yes. In the structural application, I need to apply a structural theory. And the theories for large deformations of beams and plates refer to an undeformed reference configuration. You can, of course, transform this to the Eulerian framework, but the usual kinematics of beams tells us we refer all our quantities to the places of the axis in the reference configuration. And this is clearly, and this is also how one can derive, for instance, nonlinear beam theory from continuum mechanics most easily in the Lagrangian, in the material framework. So this was the motivation to apply it later on in the laboratory to structures.
Another question? I have a question for you, Anne. Oh, sorry. Please.
May I ask a short question? It's even on the slide. You mentioned that if these KANN are not known or something like that, you need an extra automatic control. This is what you said. What you mean and what's... have you any specific control law in your mind?
Yes. If something here is not known, yes, you cannot solve this problem exactly, yes. But usually this MA is produced by some piezoelectric patches or similar things, yes. And then you must measure the response and must connect this output by means of a control algorithm and to feed back the corrected value. Yes, and this has been done. Yes, and you can formally add here something, and this has been done in our group in Linz in the framework of the so-called Port-Hamiltonian system control by Professor Kurt Schlacher in the last years very successfully, and his group. It's feedback then, and this is feed forward in the language of automatic control. So my solution is simply I assume the system to be known, and I ask for this additional actuation, and then interestingly enough, it was possible to find to find an exact solution for this, which however requires MA to be distributed in space and time, and this must be of course technologically then realized. Yes. Thank you for the question.
Very shortly, my question. I got the impression in the first part that the actuation was of the piezoelectric type, as you added, concentrated in some part of the body. You were speaking about actuation. But
yes, I mean, if you have a temperature loading, yes. Then you have some a temperature loading. Then of course you obtain such a actuating stress tensor PA+ everywhere in the body. And now is the question how to tailor the coefficients of thermal expansion such that this works, or how to tailor the temperature, which leads to another problem, namely a problem of conduction of heat.
So the question was exactly this: the temperature is the part of actuation or external excitation? The thermal field?
There may be forces or thermal excitation as, so to say, the primary sources, and then the thermal stress, piezoelectric stress type, additional actuation in order to suppress this or to make this to another field.
It will be concentrated or distributed, no problem.
In the theoretical solution, it then will be distributed, and this has to be discretized in a later step, which I had not the possibility to talk because we are not so far, but in the linear case, this has been realized. Yes.
Okay. Thank you again for your
Thank
presentation.
you so much.
If we have time, I would like to ask you the following question. Well, your presentation is rather theoretical, but I have a practical problem which might fit into your formalism, and which is the the next generation of space reflectors. Because the idea is to deploy in space a membrane, a very thin shell, okay?
Yes.
And of course, we cannot get the accuracy which is required for an optical system. And then the idea is to have a layer of active material and to control the voltages of piezo, for example, in order to achieve the right shape. My question is, the examples that you showed are either extremely simple as a single degree of freedom oscillator or extremely abstract as a second one. And do you think you could tackle the problems that I was mentioning?
I mean, what has been done by our group, particularly by my co-worker Michael Krommer, who will also talk about plates and how to cover plates with piezoelectric distributions in order to obtain desired deflections. And what Michael Krommer will talk about tomorrow is the theory of large displacements of these plates. So these would be a first guess for your shell type problem, and how to really physically correctly model the actuation there. Because this is, of course, coupled and nonlinear and so on. But I think it would be very interesting, and I would kindly ask for your advice, and we could possibly do something there. Thank you.